Hello, I'm Dr. David Bosch, research hydrologist at Southeast Watershed Research Lab and lead scientist for our NP211 project. The observations presented here are the results of a long-term study of the impacts of conservation tillage in coastal plain soils. We quantified crop yield, surface and subsurface flow, sediment, nutrient, and element transport, comparing conventional and strip tillage for cotton and peanut production. Some of the key findings and impacts were: there were no yield differences for the cotton or peanut crops studied. Our results indicate conversion to strip tillage reduces surface runoff by 50%, sediment losses by 85%, pesticide losses by 50%, and nutrient losses by 50%. Increased available water under strip till results in increased subsurface water loss by 70%. Net water impact is that there is no difference in total water loss. Nitrogen losses were dominated by strip till subsurface water loss. Winter cover crops reduce sediment loss and increase soil carbon and nitrogen. Strip tillage resulted in an enrichment of total organic nitrogen and carbon in the surface runoff, both by 50%. Conservation tillage is used on 70% of the cotton acreage in the southeastern U.S., and these results indicated as having a significant impact on water, sediment, and nutrient transport throughout the region. For additional information, please refer to our website shown at the bottom of the slide. Thank you very much.
Hello, my name is Michelle Reba. I'm the lead scientist at the Delta Water Management Research Unit on campus at Arkansas State University in Jonesboro, Arkansas. We are a small but mighty group of 3 SYs and a wonderful group of support scientists and collaborators. Dr. Massey and Dr. Adviento Borby are both agronomists, and I'm a hydrologist. Arkansas irrigates the 3rd largest land area of any state in the U.S., with approximately 80% of irrigation water coming from the Mississippi River Valley alluvial aquifer, which has shown signs of decline in recent years. Arkansas also grows over half of U.S. rice, and how the water is managed influences many things, including greenhouse gas emissions. Our unit works closely with producers from a systems approach for resilient rice production in the Mid-South, which is what we chose to highlight for you today. We were able to demonstrate that innovative water management in rice can reduce greenhouse gas emissions, but did not affect milling yields. Our work in greenhouse gas measurements using static vented chambers and eddy covariance, shown at the bottom of the slide, contributes to national efforts to improve our understanding of emissions. In the off-season, how we manage also influences gas production in the fields. We were able to demonstrate that winter flooding for waterfowl can equal about 25% of the growing season's emissions. We have also contributed to improving automated water level measurements in rice, which will eventually improve irrigation efficiency. Members of our group are working on a large NSF grant that discovered a gene in rice that may help protect rice from high nighttime temperatures, which can be very damaging to yield. Our group works with a broad range of stakeholders, often working at the field and farm level alongside producers to improve management. We enjoy collaboration with multiple universities, state and federal organizations, and several private industry groups. Our efforts have led to members of our group receiving 4 national awards from the Soil and Water Conservation Society, the American Society of Agricultural and Biological Engineers, the Rice Technical Working Group, and the National Conservation System's Cotton and Rice Conference. Thank you.
Hello, this is Ken Stone. I'm with ARS in Florence, South Carolina. The southeastern coastal plain region includes highly weathered soils with sandy textures, low organic matter contents, and highly variable water holding capacities. The region's crop yields are impacted not only by fertilizer management, but by large rainfall variability during the crop growing season. Often this requires supplemental irrigation. Therefore, our research is focused on improving water and nutrient use efficiency in the region using variable rate irrigation systems in connection with decision support systems. The first decision support system that we adapted for variable rate irrigation management was called Irrigator Pro for corn. It proved to be effective in managing spatial irrigations while also improving the nutrient use efficiency. The second decision support system that we worked with was part of an ARS multi-location research project. We used the variable rate irrigation decision support system called ARS Pivot that uses both crop canopy temperatures to detect plant stress and soil water measurements. This novel system had higher corn yields and improved water use efficiency than a scheduling method using only soil water potential measurements. In a separate study, we measured the crop canopy reflectance using NDVI to estimate irrigation crop coefficients to develop prescription maps for variable rate irrigation systems. We did this for both cotton and corn. Finally, we developed a set of rainfall probability tables to inform growers and extension practitioners on the potential for rainfall extremes in the region that should be useful for both irrigated and dryland agriculture. Thank you.
Hello, I'm Paul White, the lead scientist for the NP211 project at the Sugarcane Research Unit in Houma, Louisiana. I also wish to introduce Dr. Patrick Ellsworth, a research plant physiologist who joined the project in April 2020. About half of the U.S. sugarcane crop is grown on 195,000 hectares in South Louisiana at a value in 2019 of over $830 million. Louisiana production is unique in that we grow sugarcane, a C4 tropical grass, under the most temperate climatic conditions in the world, including a winter dormancy period. Annually, we receive over 1,600 millimeters of rainfall, making the coastal ecotone one of the wettest in the U.S. Frequently, crop management is limited by excess rainfall, low elevation, and reduced infiltration. Therefore, over the past 4 years, we've created a network of eddy covariance flux towers, meteorological and soil sensors, and research collaborations to study how the hydrologic properties influence sugarcane production. An example of our work is presented in the slide. By combining spectral information from remote sensing with eddy flux and plant growth measurements, we've calibrated a vegetation photosynthesis model to estimate GPP. Field-level data indicates that sugarcane has the potential to sequester as much as 5 tons of carbon per hectare in the soil per year. However, we've also discovered that crop ET is not as strongly influenced by row spacing as previously thought. Therefore, our future work will focus on elucidating the controls on agrosystem water use efficiency, including predicting which characteristics are most related to high biomass production and water use. This work will go beyond sugarcane and be used to characterize crop water use in other water-abundant environments.
Hello everybody, my name is Ruixiu Sui. I'm a lead scientist of Sustainable Water Management Research Unit in Stoneville, Mississippi. I am presenting the selected accomplishments of the research project, development of sustainable water management technologies for humid regions. We developed and evaluated variable rate irrigation technology for irrigation water management in Mississippi Delta. VRI prescriptions were created based on soil electric conductivity, and irrigation was scheduled using sensor-measured soil moisture. Desired amount of water was applied set specifically according to the VRI prescriptions. Compared to uniform rate irrigation, variable rate irrigation saved up to 30% irrigation water. We developed low-cost sensing devices to remotely monitor crop and weather conditions. Real-time monitoring of field conditions was accomplished by accessing the internet available data. Those inexpensive sensing devices could enable researchers and producers collecting field data with a low cost. Using the eddy covariance and residue energy balance method, we quantified water and carbon dioxide fluxes and water use efficiencies in corn, soybean, and cotton crops in Mississippi Delta. Results of this study are useful for irrigation scheduling and adapting crops mixtures that are environmentally and economically sustainable, conserving limited water resources in this region.
Good afternoon. I'm Eddie Longedoen, lead scientist for the ARS research project Managing Water and Sediment Movement in Agricultural Watersheds, which is managed by the Watershed Physical Processes Research Unit in Oxford, Mississippi. Soil erosion, or erosion in general, is a major focus of our research program. My colleagues and I have conducted laboratory, field, and numerical experiments that advance both USDA's understanding and prediction technology of erosion and sediment transport processes. Among others, we produced new relations on the dimensions of eroding ephemeral gullies and their networks, and demonstrated the accelerated erosion caused by interactions between ephemeral gullies and soil pipes. Acoustic-based sediment transport measurement techniques were enhanced to measure coarse bed load by grain size in streams. We quantified the effects of wind-generated waves on shoreline erosion of on-farm irrigation reservoirs. This new information has directly led to improvements of our erosion models at the field scale Russell II, at the watershed scale NCNAPS, and concepts in BSTEM for channels, shorelines, and embankments. Russell II is critical technology for USDA. It ensures farmers are compliant with conservation planning stipulated in the Farm Bill and receive financial support for soil conservation. NCNAPS is used by EPA and NRCS to develop targeted conservation measures that conserve soil and improve ecosystem services in agricultural watersheds. Our stream-related measurement and modeling technologies are being used across federal and state governments, for example, to identify the risk of failure of near-stream agricultural infrastructure, to plan and evaluate large flood control projects, or the removal of large dams to restore streams. These projects represent a combined $5 billion of federal investment. My colleagues and I are ready to tackle the issues facing U.S. agriculture over the next 5 years. Thank you.
Hello, I'm Richard Lazat, Research Ecologist with USDA. This is a brief summary of accomplishments and impacts from the Water Quality and Ecology Unit in Oxford, Mississippi. Today I will focus on our long-term conservation effects assessment project watershed, Beasley Lake in western Mississippi. The watershed has implemented multiple USDA NRCS conservation practices, including vegetated drainage ditches, a vegetated sediment retention pond, vegetated buffers to attract wildlife, and conservation reserve program set-asides, CRP. To measure improvements in water quality due to these conservation practices, we assess reductions in total suspended solids, TSS, and nutrients, total phosphorus, TP, and total nitrogen, TN, on surface water runoff. With vegetated ditches, we saw reductions of 72% for TSS, 65% for TP, and 59% for TN in runoff. Within the sediment pond, we saw reductions of 88% for TSS and 62% for TP and TN. Runoff through buffers showed reductions of 65% for TSS and only 19% for TP and 36% for TN. We saw greatest reductions in runoff through CRP, with more than 90% for TSS and more than 70% for TP and TN. These improvements in runoff water quality impacted lake water quality over 25 years of monitoring. Since monitoring began in 1995, lake TSS decreased by more than 95%, TP decreased by nearly 70%, and nitrate decreased by more than 85%. However, TN appeared unaffected despite clear reductions in runoff. Conservation practices have clearly improved water quality in runoff and lake water in Beasley Lake watershed. Thank you.